Okay, so I introduce you the chapter 26.6, which is about the dot between two vector. We don't multiply two vector. So I post this one for you to maybe you watch at home, because I want the next few class you focus on your IA to make sure you have produced a good paper IA. Okay, so we do a lot of time we do in class the IA, and this one you can do at home. Okay, so now remember the vector is we call a vector value function. When you put some number in the vector, you come out to be the vector. And unlike the function, regular function, we real number function, also the scalar. So you put the number into any function we learned so far, you come out to be have some number. The answer we call a scalar. So in this case, so the dot products turn two vector into the scalar in such a way like this. So definition. I do 2D first. Okay, 2D first. If A, vector A equal A1, comma A2, and vector B equal B1, comma B2. Now we say, okay, we define A dot B equal A1, B1, A1, A2. A2 dot with the vector B, which is two component B1 and B2. So now the operation like this: A1 times B1, A1 times with B1, and add with A2 times B2. You can see clearly this one come out to be number, no more vector. Okay, because A1 is a number. It's a number. When you multiply, you get some number. So this one is scalar. Okay. The answer of the result of the dot product turn two vector into the scalar. Now we remember the pure math perspective. They make up many cases. They make up. Let's call it a dot product. For some reason they foresee what happened next. And after you make up that definition and okay, what the probability after this? So people create a whole lot of theorem, and we can apply to solve a lot of problems. Okay, so we just take for granted at this moment. So now in 3 dimension, so observe the 3 dimension, you get A1, comma A2, comma A3. You dot with B dot. The point here with the dot here we call the dot. Obviously B2, B3. So you dot, you're going to have A1 times B1 plus A2 times B2 plus A3 times B3, B sub 3. So this one here, 3 dimension, and we will discover what that means in the world of geometry. Okay, so here is a definition of the dot product. So now, take a look at this. To the left here, we have the whole bunch of property. Okay, so they say if I have the vector A dot B had to be equal B dot A. So to see how it works, okay, take a look at this. So I have A dot B equal A1 B1, right, plus A2 B2. So since this one now is a number, you can revert operation, right? A times B equal B times A, right? So that's what we call the commutative of multiplication. From very early algebra we learned, we call the axiom. So equal B1 times A1 plus B2 times A2. We flip over using the property of multiplication, commutative of multiplication. So this one turned out to be, go backwards, some to be B dot A. Okay, so A dot B equal B dot A. So that's the first property after you give the definition of the scalar dot product. So this one very easy to simplify. Okay, to check. So now number 2, I have A dot B, right? So I have A dot B that. If I multiply by C, okay, it's going to be what? I multiply by C after I dot A dot B. So this is going to be C times the whole thing here, right? So it turned out to be C times A1 B1 plus C times A2, B2. C is a number, this one also the number. So now, how to show C equals CA time dot with C? So you get CA here. So this one equals CA. CA1 is CA1. CA dot B. Okay, so now in this case, you have C time with A dot B now. We work it out C time A first and you dot with B to see what happened. C time A, you still, if C time A, you still have the vector. Okay, it's going to be the vector. So now C time A equal C A1 A2, right, equal CA1 comma CA2. So this one still the vector. Now you dot with B. So dot with B mean then you dot with B. Okay, dot with B mean you dot with B1 comma B2. After you dot, it's come out to be the number. So this one by definition again, this one times this one, CA1 B1. Okay, you add with CA2 B2. So this one here just the same with here. Okay, just the same with this. So you can easily to verify the property using the same relation, right? You add two vectors, you still have the vector, and you dot with A, and instead of that you dot A dot B, then you add with A dot C. I leave this for you to verify. Okay, just take a piece of paper to verify all of them. So the benefit is when you verify things, you remember and you understand deeper rather than you remember the formula. So always you have to check. Okay. Okay. So now the next one is the most important one. This one leads into something else. So the last one I saved is here. This one here, the most important here. They say A dot A equal absolute of A square. Okay, A dot A equal absolute A square. Now to see what happened, we want to prove it, right? So let's say A is two dimension. I have A1, A equal A1, A2. Okay, so now A dot A. So A dot A itself equal A1 comma A2, that is vector A, and you dot by itself. So another A1 comma A2. Okay, so equal what? So A1 times A1, which is A1 square plus A2 square. Now, what does this mean? So remember, if you have the vector here, vector A here, right? The distance, the train of the vector here have to be A1 root of A1 square plus B1 A2 square, right? You have two components here. So the absolute of vector A equal this. So in this case, this one equal absolute of vector A square, which is give you A dot A equal absolute A square. Okay, so A dot A equal absolute A square. This is the most important property in all four of them. Very important. So always you have to remember this. Okay, A dot itself equal the absolute equal the magnitude of A square. Okay. So now after we present the dot product definition with some property, right? We led into some most important theorem in dot products. Here the theorem say, if I dot A dot B between two vector, if I dot A dot B, so I'm going to have absolute of A, the length of A, times absolute of B, the length of B, times cosine theta. So the cosine theta here. Okay. So now how to prove this? So also equivalently, you have cosine theta equal A dot B divided by absolute A, absolute B. Okay. Okay, now I change a little bit. This one I write with the normal letter. I have to put the arrow, right? But when I do the bold letter, so this one is the same with vector. Okay, this one look better. Okay, absolute B. So now in short, in the other way, if I know angle A, if I know vector A and vector B, we can find the angle between A and B, okay, using you dot A and you dot B and you divide by the length of A times length of B. So now we prove this theorem now. So first of all, this one here I mentioned is the most important property of the dot product. So we can derive the formula based on what we already proved here. So now we use the law of cosine. So the vector here could be, you can do both directions. Let's say A minus B, or A minus B means you have thought vector B minus A, you get another vector, right? So vector A minus B. So now if you take the absolute value, so all absolute value, so this one we can use the law of cosine, right? So the opposite is A minus B, okay, square equal A square plus B square minus 2 times A times B cosine theta, right? This is the law of cosine. The opposite line square equal this line adjacent square plus this square minus 2 times A times B cosine theta. So what does it mean? This one, look at this. This one a substitute for the vector A, right? So absolute vector A square equal A dot A, that means A minus B, you dot with A minus B. Okay, you dot two vector, right? The absolute go backward here, the property here apply for this, and we take the whole thing here in terms of this A, and this one here in terms of this A, right? Okay. Okay, so now equal to the right side you have A square plus B square minus 2A B cosine theta. This one comes from the law of cosine. So now when you dot this one, mean A dot A, okay, minus A dot B minus B dot A. Finally you get plus B dot B. Okay, this one vector, this one O vector. Okay, so A dot A, again A dot A equal A square, absolute A square, right there. And this one you minus 2 times A dot B, because we already say A dot B equal B dot A, right? A dot B equal B dot A, therefore you have 2 times A dot B. Okay, this one still a vector. Okay, yeah, vector A dot vector B, this one vector A dot vector B, vector A dot, but later on this one turn out number. So plus absolute B square, so based on this one here, B dot B equal absolute B square. So the right side is come from the law of cosine, B square minus 2 times absolute A, absolute B cosine theta. So now we cancel this one, you cancel this one, cancel this one, cancel this one. Also you cancel negative 2 divided by negative 2 both sides. So it leaves you A dot B equal absolute A, absolute B cosine theta. So you have that, you reach that equation, okay, that theorem. So also you divide both sides by A, B, then cosine equal that. So two of them equivalent. Very important, very helpful, very useful in the future. You use a lot of this to solve the problem, okay. So here is